Good afternoon, everyone, and welcome. I'm Aishwarya, and I'm a postdoc from Kathuria and Gracias lab at the Johns Hopkins University. Today, I'll be talking about my doctoral research in Dr. Gracias's lab on how we can embody morphological intelligence in 3D microfabricated devices, particularly for applications in bioinspired soft robotics. When we talk about intelligence, we often think of the brain, of cognition and problem solving. When we look at our world, intelligence appears across all forms of life and not always the ones with a brain. From the reactive movements of a carnivorous plant to grab an insect, to the emergent choreography of birds flying across the sky going back home, to the social learning in primates, and even the intergenerational memory and communication we see in humans. These are all examples of how living systems sense, adapt, coordinate, and evolve. And naturally, humans started mimicking nature when they decided to build things. So, when we think about intelligence in materials and systems, it is a progression that has happened as humans have evolved. So, mechanical systems came first. These systems rely on external intelligence, which means that they work and have a specific function, but only because someone is sitting behind it and operating them, pushing the buttons and setting rules. Then came the inherently intelligent systems, which do not need an operator to control them. This intelligence and their functional reaction is embedded in the molecular structure of the material itself. These materials are stimuli responsive systems that swell, shrink, fold, or react in response to different environmental stimuli like light, heat, or chemicals. Pushing further, we arrive at embodied or morphological intelligence. These systems interact with their environment based on form and material logic. This intelligence is not just in what they were made of, it is also how they are shaped and how the shape interacts with the environment around them and determines their functional behavior. This is my story today. Untethered gel robots that can essentially pick a side and crawl in that direction. One of the materials used for soft robotics, which is the focus of my story today, are hydrogels. These squishy gels are found all around us in things like jello, aloe vera, or even our contact lenses, for instance. These gels are not only flexible and lightweight, but have the potential of biological augmentation. All around us, biological organisms like us mostly comprise of water. Similar to that is a hydrogel. A hydrogel with its porous network can swell in and take more than 70% of water. Also, organisms all across nature are built out of soft and stiff elements. Based on polymer backbone and how densely you can cross-link, the hydrogel stiffness can be tuned in the ranges, especially from really soft brain tissue to smooth muscle-like tissue, like on an artery. One of the biggest issues of building conventional robots is how do we consistently power them, especially when we size them down. In our case, how do we power a gummy bear-like robot? The answer is simple. These materials can power themselves. Stimuli responsive hydrogels or gels with embedded intelligence in them can reversibly swell and take in water and shrink and expel water in response to certain environmental stimuli. These volumetric transitions happen because of coil to globule transitions within the molecular structure of the gel. These gels can be programmed to the environmental cues like temperature, light, electromagnetic field, and chemicals. Combining these materials with design principles, we can actuate the program structure to perform complex functions for a wide range of applications. Hence, using stimuli responsive hydrogels, we can create autonomous robots that are both untethered and powered without an external battery, thus embodying intelligence. This is something I worked on particularly in shape-changing structures during my master's studies at the Johns Hopkins Universities. This story, however, focuses on thermoresponsive crawling. With our materials established, let's segue back to soft robotics, particularly hydrogel robotics. For any actuating system to move, it has to break symmetry. We see this when we walk as well, where we break symmetry with one foot as an anchor and the other foot swinging. In soft systems, especially with two material ones, this was often done using bilayers that bend when they swell differently. Let's look at what came before. Early hydrogel crawlers could break symmetry, but only conditionally. Nearly all of them relied on engineering terrain, which is ratchets, channels, or confined tubes. Anywhere else, they would flop and stall. That was the challenge I took on. Can I embody intelligence into the building blocks of a robot so it can guide itself without any surface modifications, using just two materials and a global stimuli? Now, if you start with a simple bilayer and it swells and deswells, it will do so symmetrically, which means you get no displacement. So, to solve this problem, I looked into biology, specifically peristaltic locomotion like we see in worms. Or honestly, the much cooler example, which was a breakdance step that my advisor Dr. Gracias pulled up in a meeting, and I was immediately lured by his idea. So I thought, what if we connect two bilayer segments made of the same materials but with different thickness ratios and geometries and join them with a linker? I hypothesized that this would generate a asymmetry in swelling that would trigger a asymmetry in the structure of the device while it deswells and move the robot ahead as it does. So as a first year PhD student, I was faced with two grand challenges, which was surviving all the chemical engineering coursework and the more relevant practical implementation of my lofty idea. I was faced with a lot of critical questions, which was which bilayers do I use? And if I did use them, what dimensions did I want? What thickness ratios did I want? And if I was connecting these two bilayers with a linker, what would be the design of the linker? What would be its length, its width? And if I wanted this linker to be suspended or I wanted this not to be suspended. And after creating quite a structure graveyard, or at least what I call all the iterations of robots that didn't work, I finally started getting some answers. Before getting into any results, I would like to go over how I actuated all the bilayers and robots. I first printed and cured my robots and then placed them in a tank filled with water set on a hot plate. And I first allowed these robots to swell and curve in a cooling half cycle where they swelled at 25 degrees and then through I allowed them to deswell through a heating half cycle at 60 degree where they deswelled back to the flat position. These two steps constituted a thermal cycle. So how do I fabricate these gel robots? I used a 3D printing technique called direct ink writing, which uses a pressure-based extrusion mechanism to print my hydrogel inks. My hydrogel inks were modified to have the consistency of toothpaste and they were piped on top of each other to create layer by layer to create the structure. After printing the structure, I put the printed robot through a UV curing step to polymerize the hydrogels in the structure. Now let's move to the polymer chemistry of our inks. I prepared two differentially swelling gel inks, an active gel or swelling gel and a passive or non-swelling gel. Both gels were prepared with water as the solvent. I used NIPAM, which has isopropyl groups on its polymer backbone that make it thermoresponsive. As you can see in the figure, any structure printed with this gel would swell and deswell in response to temperature. For our passive ink, we used polyacrylamide, which is not thermoresponsive because it lacks that isopropyl group. I added a crosslinker to make it stiff and low swelling. And to allow both inks to be 3D printed, I added rheology modifiers like laponite to make its consistency toothpaste-like and pipeable. Because I was using UV cross-linking to cross-link my structures, I added a photo initiator like ErgoCure. So the way direct ink writing works for printing multi-material structures is by switching printer heads and printing the entire layer and then moving on to the next, layer by layer. This is how I ran into my first challenge. I had two printer heads, but I planned to print with three materials. This is because I needed to print a sacrificial layer under the middle segment to support it. Since I couldn't add a third nozzle to my two material printer, I had to manually switch the cartridges mid-print. So I had to find a way to do so. To make it work, I edited the code of the printer to print the laponite first, slowed down the travel speeds to give myself time to swap, and then use the same nozzle for both NIPAM and laponite, and then cleaning it with air and water in the middle. And then I let the print go on as it was supposed to. To pick the two bilayers I wanted on either side of the linker, I needed to understand the morphological characteristics of the bilayers while they were swelling and deswelling. To do this, I systematically varied the thickness ratios of the bilayers, which is the ratio of the thickness of p-NIPAM to the ratio of the thickness of polyacrylamide, and put them through a thermal cycle. After they swelled completely, I mapped 3 points in the bilayer to, to figure out what the curvature of the bilayer was after it swelled. As you might intuitively expect, thinner the bilayers, they bend more, they respond faster, and they generate greater curvature. I'm just showing two bilayers here, but the trend was consistent across the board. Now coming to the main part of the story, to build the crawler, I connected a small and a large bilayer using a soft-smelling p-NIPAM linker. We actuated the robot by cycling the temperature between room temperature and 60 degree, like I mentioned a couple of slides ago. During the cooling half cycle, which is images 1 to 3, the mismatch in the swelling caused both bilayer segments to curve and bend upward, while the linker sags downward and touches the floor. Since the linker had the largest contact area, it anchors the robot and both bilayers move towards it. The red arrow denotes the anchor of the robot. Then we switch to the heating half cycle, which is images 3 to 5, and the smaller bilayer and the linker deswelled more rapidly and began to straighten. At this point, the anchor shifted back to the larger bilayer, which retained more curvature, and the deswelling linker then acted as, while it was deswelling, pulled the other bilayer towards it and moved the entire robot ahead. This entire sequence results in a unidirectional motion of the robot at 4.4 body lengths per cycle. We collaborated with Dr. Vicky Nguyen's lab at the Johns Hopkins University to run finite element simulations on the robot's actuation over a thermal cycle. What you see here is the normal force on each segment, which is the two bilayers and the central linker, plotted against the normalized actuation time. Since this graph looks really busy, let me unpack it a little. Now, the segment with the highest normal force at any point effectively becomes the anchor. At the start, when the robot is in a flat state, the larger bilayer shows the highest amount of normal force simply because it's the most massive segment. Then during the cooling half cycle, the bilayers bend and push the linker downward. This causes the linker to experience the highest normal force and thus the highest friction force. You'll notice that the normal force on the bilayers drops by 50% while the force on the linker quadruples. This is what makes the linker as the anchor and draws both bilayers slightly towards it displacement wise. Next, we heat the robot to 60 degrees. As it heats up, the linker deswells and lifts off the surface, and at this point, the larger bilayer, there's a cross off between the normal force, and the larger bilayer again carries the most normal force and becomes the anchor, and the smaller bilayer and the linker that has not completely deswollen will be pulled towards the larger bilayer, producing a net unidirectional motion. So what we demonstrate here is that asymmetry in contact forces governed by segment morphology and thermally induced shape change is what is driving our robot. The robot mechanism established, I wanted to try to tune the displacement of the robot. I hypothesized, but by increasing the contact force asymmetry between the two ends of the robot, I might be able to trigger more displacement. And I wanted to do this by using the design of the robot itself. So in the previous robots, all the three segments, the two bilayers and the linker, participated in actuation. So I asked, what if the linker did not participate at all? And I wanted to see what its effect would be on the contact force asymmetry. To test this, I kept the bilayers the same, but made the linker 15 times stiffer by using pure polyacrylamide as the linker. This new linker barely deformed and did not touch the floor. Without the linker contributing to the friction, the asymmetry between the bilayers increased and the robot moved faster, which was 5.1 body lengths per cycle, up from the 4.4% which we got from the soft linker. So by preventing the swelling in the linker and by preventing it from interacting and taking away the contact force asymmetry, I actually improved the performance in the robot. Another thing I wanted to establish was that the actuation direction is entirely dependent on the orientation of the robot's bilayers. So I put the robot through 10 cycles forward, rotated it around and put it through 10 cycles backward. So essentially what we proved is that the robot would always consistently move to the side that has the higher symmetry. Next, I wanted to see if I could induce even higher contact force asymmetry by varying design parameters like number of bilayer segments and changing the design of the linker and the linker pattern itself. In our earlier designs, the linker were either largely active or largely passive, and both felt a little wasteful. I wanted to get a bang for the linker buck. So I asked, what if I designed the linker that could elongate but still maintain mechanical integrity? So I developed a design in the linker design in a way that it was made of alternating strips of polyacrylamide and PNIPAM. The idea was that this composition would let the linker stretch without sagging while also increasing the contact force asymmetry. And I also increased the number of bilayer segments to two small bilayers on one side and one large bilayer on the larger side, now making it look like a lobster. And this robot did work, and this robot moved at 7.8 body length per cycle, which was a significant improvement on the previous robot at 5.1% body length per cycle. And taking it up a notch, keeping the same alternating linker, but now with four legs, two small and two large bilayers. And this increased the contact force asymmetry even more. And this final robot reached 12.2 body lengths per cycle and ended up being our best performing robot. In sum, I developed a mechanism that exploits the robot's own geometry by engineering morphological asymmetries within the structure itself to generate unidirectional displacement without needing any patterned surfaces. In other words, the robot doesn't need any surface patterning, it just picks a side and goes. I also demonstrated experimentally and simulation wise that both contact force asymmetry and displacement can be tuned by adjusting the linker's morphology and also the number of bilayer segments. What we are doing here is embedding a form of gate not just through programming but also through the design of the structure and just material. As for the future, I hope we can build robots made from multi-stimuli responsive hydrogel, thermo, bio, chemo, and mechano-responsive so that they can be triggered uh, by far more complex environments and inputs, and would it also be exciting to see these robots integrated with feedback mechanism, chemical and sensor payloads, and also complex structures and interfacing it with tissues. So these robots one day would be able to carry and deliver payloads, whether it is in the human body, under the sea, or in everyday applications like plumbing. And especially with the interfacing of these hydrogel-based robots and living tissues, we open the door to something new, biological intelligence. This is where engineered platforms merge with living systems to create devices that would be able to sense, adapt, and even evolve. And there's already progress towards biological intelligence where soft materials like hydrogels have been interfaced with muscle tissue, like in panel A and B, to build biobots that can walk when stimulated. And in pattern C, uh, hydrogels with cardiomyocytes beat and mimic butterfly wings, changing color and moving dynamically. Together, these systems highlight a future where materials and tissue can not just passively exist but actively move, sense, and adapt, bringing us closer to embedding biological intelligence into soft robotic devices and biomedical tools. I would like to thank NSF for providing funds for this research and my advisors and other collaborators in the project for their input and help.